Second weekend, what are we gonna look at this week, Millie? So, I originally was planning on looking at quantum mechanics and the theory of relativity. Have I studied physics since GCSE? Since I was 16? Did I think I could learn? Not a lot, but a lot as well within a week. Maybe I did. Anyway, this week we are just going to be talking about quantum mechanics. Theory of relativity kind of does go into it a tad because of Albert Einstein, but apart from that, we're not talking about space. We're not talking about the speed of light, E equals mc squared. We're not talking about that. We're talking about micro atoms. We're going to be talking about quantum this evening. Okay, getting comfy in my chair. Basically, we start off with classical physics. So classical physics is the study of the physical world. It is the involvement of gravity, motion, and electromagnetism. In 1687, the modern physical science was established through Sir Isaac Newton's Principia, which outlined the fundamental laws and the kind of philosophical standpoint of the world of that time. Then the Principia is the assumption that at the current time, there was sufficient information to predict the future behaviour of the universe. So this is the concept of determinism. An example of this could be the solar and lunar eclipse, which occurs how many years? And it's like the clockwork universe concept. So the concept is, if you know the exact position, the exact momentum that all the particles in the universe had at that very moment, then you can predict, in principle, when or if ever it'll occur and how and like where. What, when, where, why, how. After Isaac Newton came, well, there were others, but there was James Maxwell, who paved way for the special theory of relativity. His ideas ushered movements and expansions of scientific theories that also ushered into 20th century physics, i.e. quantum physics, or the quantum theory. Basically, his electromagnetic theory was able to lead to quantum theory because his description of electromagnetic radiation made Maxwell Planck delve into the kind of unstable, but wasn't really established, but law of heat radiation, and formulate the quantum hypothesis, which is the theory of radiant heat energy is emitted in a finite amount or quanta. So it's not continuous, there is an end and a start. Well, there's a start and an end. Radiant heat energy is not smooth or nor continuous. So rather than if you imagine tap water, it can be constantly flowing. He's not proving that. He's proving that it's coming in droplets, and you can kind of alter if you want more or less of droplets, but you can't half a droplet. After Max Planck's hypothesis, you have Einstein's concept of photon, and you have Bohr atomic model as well, which is the old quantum theory. So basically, in essence, quantum science explores and helps explain the strangest myths, the strangest mysteries. I'm mixing up my words, but the strangest mysteries of the universe at an atomic scale. As Cambridge explains it, it's a theory that explains the behaviour of elementary particles both separately and in groups. Basically, it helps us understand the scientific phenomenons around matter and light at an atomic scale or a subatomic scale. Explores behaviours like wave-particle duality, superposition, and quantum entanglement. So quantum entanglement is when two or more particles become linked, and it's one of the most far out phenomenons of quantum theory. Einstein kind of called it a spooky action at a distance. It's the idea that particles of the same origin, which were once connected, are always going to be connected. So like if you think of like the red string theory, like imagine, like this is not linked to physics, but no, this is linked to physics. But like the red string theory is like everyone is connected and you can't cut the string. That's basically what it is. You can like separate, you can be as far away from each other, but you're always going to be connected and there's nothing that can cut it. But with quantum entanglement, it also conflicts with Einstein's theory of special relativity. The contradictory fact is that the information of quantum state would be that it'd have to be delivered faster than the speed of light, because for the particles to instantaneously come together. And with the quantum entanglement, you can also link it with the Stratoginger wave equation, which is developed in 1926 by an Austrian physicist called Edward Stratoginger. And the equation basically describes the behavior of photons, electrons, and it describes how the wave function, which is a mathematical tool in describing the state of particles, how it behaves. And it's an equation that's developed by the renowned experiment of the double slit experiment, which shows how light behaves as a wave, thus providing that it's a particle and a wave. Combination. The duality, though, it cannot be simultaneously observed, so they can't observe the light particle as a wave and as a particle. Yeah, they can't see it being like a singular and a double plus, because it obscures the wave-like nature and vice versa. So interesting. It's actually really interesting. I hated this. I hated studying, or like not studying, just researching in my own time. I literally was looking and reading up all of this and just being like, and I was questioning why I actually was researching physics. Who knows? Who knows? So basically, with this double experiment, when I was researching what it actually was, if you imagine two walls, I'll put a picture of the picture, like here. If you imagine, say, okay, they used a tennis ball. So if you throw a tennis ball through one of the splits, you'd assume it would kind of go there. And if you carry on throwing it through the same split, then it will just carry on entering and going into the same position. And if you do it through the other space, it'll kind of do the same. Okay, but if you show this in the quantum realm, should I move over here? Okay, I'm gonna have to read. So you open the splits and you'd assume it may be like the tennis ball, but no. With the two splits, actually, you would throw the electrons, the neutrons, protons, they wouldn't be straight, they'd kind of go towards each other, creating a third space. This is what I gathered. And it is basically because of quantum entanglement. It didn't say that, but it literally is quantum entanglement. So if I'm wrong, fucking tell me I'm wrong and I'll learn it and I'll really appreciate that. It shows that all of these electrons, protons, whatever atom they used, are all connected. They're all connected. When they replicate the interference, blah 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 blah. I don't understand half of this shit. I've only been learning about quantum physics for a week. Okay, less than a week, I can't lie, I've been doing it like an hour daily. That's still quite good. I was really going into the history, and I've forgotten a lot of the history. It's not an entanglement in my mind. Wait, it is an entanglement in my mind. It's an entanglement in my mind because it tangles up. Sometimes I like read stuff and I'm like, yeah, I get it. And then I'll read my notes and I'll be like, what the hell, Millie? I was listening to podcasts as well, and I'll be listening to it halfway through, which would be like 45 minutes into the podcast, they'll be like, by the way, please listen to episode 8 because this will be a lot more understandable if you did. I haven't watched episode 8, so I look at episode 8, 3 hours long. I was watching as well Dr. Brian Cox, and I was thinking, the girl's going to learn quantum physics in 22 minutes. The girl did not understand anything for 22 minutes. Maybe I should rewatch it. Maybe I will now. I think I'd understand a little bit. I've learned as well, one whole day I was learning about black holes. I don't like space. And I've learned there's a black hole somewhere, I don't think in our universe, in a separate universe, separate galaxy, 6 billion times the sun in size. And as well, when black holes absorb stuff, it raises information. And we've kind of got to think that as, what the hell? And it's like as well, the lifespan of the universe, there is one. We're not just gonna be like, okay, we're gonna die, everything's gonna die, but then relive. But the universe is also gonna die. Because our universe emits energy, it shrinks or it changes. Thus meaning we're gonna die. Anyway, I was learning a bit about that. I was learning about that before quantum, or during quantum. I kind of got a bit sidetracked. Today I learned about freedom, free will, but in physics. Like, okay, I know I'm going off a little bit, but brain teaser for anyone watching this. Do we have free will? And you may be like, duh, I had free will by watching this video and I kind of wish I hadn't. It's like, okay, how do I describe this? Thinking we have free will is like a perimeter of ignorance, because we assume we can do something, yeah, there's always limitations. So, as well, I found out in medieval times, people who had like epileptic shocks, they thought they were possessed. And as well, when you ask people who have epilepsy, can they stop that? No, that is not free will. And there's other like depression or like mental disorders, me having fucking dyslexia, me having learning difficulties, people having learning difficulties. It's not a choice. Sexuality, not a choice. It's not free will. So how can you argue there is free will in this life? You could. Okay. Devil's advocate, imagine little devil on my shoulder. It could be like, maybe, but it's your choice to do anything you want. Like, it's more you have options. And by having options, you have free will to choose what you want in life. Just everything can be relating to free will. And it's as well as like, if you do have free will, is that going to implicate others' freedom? By expressing your own free will, are you going to destroy others' freedom? Okay, it's the next day, but I want to talk more about quantum physics. So,
oh my god, I'm so glad I did. I went on a bloody run. Jeez. Black holes and freedom, man.
basically, going into Erwin Stratoginger.
We are looking at how to pronounce the name of this Nobel Prize, Schrödinger. Erwin Schrödinger. You don't want to stress on the first.
So, Erwin Schrödinger also dabbled into the topic of superposition, quantum superposition, which is basically when two waves overlap, and from what I gathered, they can either interfere with each other or they can cancel each other out. And basically, he devised a experiment to show the implications of it and the implications of quantum measurement. Just cap. If you imagine a radioactive atom, it can simultaneously be decayed and not decayed until you look at it. It can be two states at once. So, in the experiment, if there's a cat in a box, it can be simultaneously dead and alive, which is superposition. You don't know what it is until you open the box.
Okay, I then go on and make no sense. So, I am re-recording this on my laptop. And well, the point I'm getting at is, because the cat is two states at once, it's both dead and alive, i.e., what an atom would be if it's decayed and not decayed, superposition. And the whole experiment to show the implications of superposition is having a cat in a box, and there's also a gauger for the atom to test whether it's decayed or not decayed. Because if it's decayed, it's going to release some radioactive energy, and by doing so, the gauger will be triggered, which will trigger a hammer or poison, killing the cat. A little bit extreme. But then if the atom's not decayed, there's no poison or hammer on the cat, but the cat could also be dead because it was in the box already dead. This is basically what it shows. It shows the implications this whole concept has. And boys, got me confused. Anyway, that's all for today. Hope you guys enjoyed.